Hi everyone, we're going to switch gears ever so slightly and talk about multiple linear regression. And really, this is the most powerful technique that we're going to use in this class. It also is the last technique we're going to learn in this class. You'll notice in your textbook there are a few other statistical approaches that are mentioned, including survival analysis and logistic regression. And those are important regression techniques that you can learn once you've mastered the basics of doing linear regression. And so multiple linear regression is a great way to start thinking about doing other regression techniques, whether it's logistic regression or survival analysis, where we would include multiple variables. Some of the same considerations are going to come up in multiple regression. So last time when we were discussing linear regression and comparing it to correlation, we really only included examples where we had a ratio or interval level independent variable. We're always still going to have an independent or ratio level dependent variable. We can, however, include dichotomous predictor variables in a regression model, understanding that our interpretation of those is different than if we had interval or ratio level measures. So mathematically, there's nothing stopping us from including dichotomous measures in a linear regression model. Our interpretation of them is slightly different, however, in that we're going all the way on a scale from nothing to everything, from no to yes. And so if you think about a regression equation, we have our coefficient and we have our value for x. In the case of a dichotomous variable, let's say it takes on the values 1 and 0. Well, if x equals 0, we multiply that by a coefficient, it's going to be 0. So that'll just wash it out. If the value is 1, which is the only other possible value for this dichotomous measure, it would simply be the coefficient in that model. So we can include dichotomous variables. And as we'll see, we can actually include categorical variables of multiple categories using an approach which we're going to discuss here shortly. So there is some flexibility with regression models that we don't have with correlation or other bivariate analyses. However, we need to be careful in how we interpret those coefficients. We can use what's called dummy coding or indicator coding to represent category membership. So a dichotomous measure, we have this variable representing yes versus no. We can also do that for membership into multiple categories. The strategy for doing so is a little bit more complex. So let's say we have an original variable called obesity status, which really technically is an ordinal measure. We have normal weight, overweight, and obese. And let's say we have it coded originally 1, 2, and 3, where 1 equals normal weight, 2 equals overweight, and 3 equals obese. What we can do is create 3 separate indicator or dummy variables representing group membership in each of those values or categories. So we would say for normal weight, we'll set it to 1 if obesity status equals 1, and to 0 for all other values. Likewise with overweight, if overweight equals 1 if obesity status equals 2, and 0 for all other values. And then we'll do that for obese. Now we have 3 separate indicator variables in our data set representing the 3 categories. Often it's a good idea to retain the original variable just so that we can have options and flexibility in our data set. But now we have these 3 separate indicator variables representing categorical membership in each of those groups. Now here's the trick. When we include these in the model, we're actually going to only include 2 of the 3 dummy coded variables in this case, or we'll always do 1 less than the number of dummy coded variables. And that seems really unintuitive at first, but what that sets up is a model where the reference group becomes the group that we excluded from the model. Okay, so if we had overweight equals 0 and obese equals 0, and our reference group is normal, then the assumption would be that they're in the normal group. We don't need to have normal represented in the data set if we're making that the reference group, because we've already set overweight and obese to 0. So as long as our categorical variable is capturing all possible values, we actually only need 2 of those to represent it in our model. And in fact, if we include all 3, it's going to blow up on us. So for a variable like biological sex, we have 2 categories. Don't forget, we only need 1 variable to represent those 2 categories. We could have a variable called male, yes or no. We don't need a separate variable called female, because female would be the reference group. So 1 would mean yes, male, 0 would mean no, female. And so in a regression context, if the value is female, it would be 0. We'd multiply the coefficient by 0 to get our predicted value. If it was for men, we would have the coefficient, multiply that coefficient by 1, and that would give us our estimate for someone who's male. So in this case, we would set up female as the reference group. The same logic applies for dummy coding for multiple category variables. Okay, so even if we were trying to represent a single variable originally, like obesity status, we would break it up into 2 other variables and then put those in the model, and then the third category would be a reference. I still suggest making all 3 dummy variables, because you may want to change around what your reference group is, but you only include 2 in the model. Okay. So already, if we've done that with a variable like obesity status, we've moved into multiple linear regression, because we have 2 indicator variables. But multi-linear regression is much more powerful than allowing us to do multi-category indicator variables. We can actually include any number of continuous interval ratio level measures. We can include ordinal measures. We can include dummy coding variables like I just described. So it's an extension of simple linear regression that allows for more than 1 predictor variable. And our understanding of health-related phenomenon and causality, often there are multiple factors involved. So especially in the health sciences, especially in medicine, we are going to want to have a model that allows for multiple inputs, multiple variables. So we use multiple regression techniques all the time in the health sciences. And so it's the most flexible in terms of allowing for different levels of measurement on the independent variables. The dependent variables still must be either interval or ratio level, but on the independent variable side, we have a lot more flexibility. We can include different types of measurement. The equation for a multiple linear regression model looks fairly similar to a linear regression model or a simple linear regression model. The difference is we're going to have multiple beta coefficients, 1 for each of our independent variables denoted here, x1, x2, x3. Notice we also have subscripts for each of the coefficients, beta 1, beta 2, beta 3. Again, this is conceptually how we're representing the model. The output is going to look a little different in the software. It's just going to have estimates for each of those different variables. Computationally, it's more complex. It's actually fitting lines in multiple dimensions, and we still let it do that work for us. But the coefficients, beta 1, beta 2, beta 3, will change depending on what else is included in the model. Okay, so unlike simple linear regression, we run it, we get our estimate, that's our estimate. As we run multiple linear regression models and we add variables to the model, we will notice that our coefficients change ever so slightly. Often that's interesting to us because it may suggest the presence of confounding, but it also does slightly change the interpretation of those coefficients. So in the case of a multiple linear regression model, we call it a conditional model. That is, our estimates for each of the betas are conditioned on other variables in the model. That was not true in the case of simple linear regression. But now what we're getting as an estimate is dependent on what we include. So we need to be thoughtful about what variables we're going to include in a multiple linear regression model. And keep in mind that our interpretation is going to change ever so slightly as we add model variables to the model. That's why we probably want to start with a simple linear regression model, get what we call our crude estimate, and then we resolve to a final model, which will be our adjusted estimate. But again, those coefficients will be conditioned on the presence of other variables. Okay? As was the case with simple linear regression, multiple linear regression is going to solve for our intercept alpha and our beta weights or our beta coefficients using the least squares criterion. Again, coming up with that best fitting line that minimizes the distance between the points and the line. In this case, we're actually doing this in multiple dimensions, so mathematics are more complicated than I'm making it sound like, but we will use computer software to do multiple linear regression. Regression coefficients are best thought of as weights associated with a given predictor when other predictors are in the equation. So it's not, when we go from that crude association in a simple linear regression to an adjusted or a conditioned model, we can think of those as how much that coefficient is weighting that best fitting line. And that may conceptually start to make this seem more complicated than it needs to. One other more straightforward way to think about it is adjusting for or conditioning on those other variables. What would our coefficient be? Okay, so once we took away the variability that was explained by the other variables, how much would our variable explain that we're interested in? So removal or addition of a predictor can then also change the beta weights. One way to determine the contributions of a particular variable to a model is to start with a bigger model and see what happens when we remove that model. We can see how much the model changes, and that's one way to assess that particular variable's contribution to the model. That's an advanced technique, but that is one way to satisfy that curiosity of how much it contributes to the overall model. The assumptions of multiple linear regression are that each variable is assumed to be normally distributed around each of the other variables, similar to how we had that assumption with simple linear regression. Again, we have an assumption of linearity with the two measures. This becomes a little more complex in the case of dummy variables, because we can't really think of it as having a linear association, but for those variables that are on an interval or ratio level scale, there should be a linear association between those variables. Likewise, we would want there to be even spread. So for each value of x, the spread of values on y should be relatively even at different values of x. So one reason we have these assumptions is that when we calculate p-values for each of our regression coefficients and the overall fit of the model, we calculate a standard error of the regression line. And the standard error of y given x is the average variability around the regression line at any given value of x. And so to be meaningful, that variability should be relatively uniform. So the standard error is assumed to be equal at all values of x for the purposes of hypothesis testing. So if we want to be able to get p-values associated with each of our coefficients, we need to have this assumption that there's even spread at different values of x. So previously we had talked about the coefficient of determination, or little r squared, or Pearson's correlation coefficient squared. In the context of multiple linear regression, we're going to have big R squared, which is the multivariate coefficient of determination. And our goal in multiple linear regression is to increase the value of R squared, meaning we're explaining more and more of our dependent variable as we add variables to the model. Okay? And it's one way that we can assess the relative predictive strength of a model based on changes in R square. And so we often seek to include additional independent variables that improve prediction, that increases our value of R squared. Realistically, depending on what the phenomenon that we were measuring, as we start to get R squares, 0.2, 0.3, 0.4, we're starting to really kind of explain the phenomenon. Getting R square values above 0.5, 0.6 are unusual unless we have measurements that are very close to what it is that we're trying to predict. So R squares aren't universally comparable, but it is one way of comparing two models to see if we've explained more of our outcome. More often, we're going to report what's called the adjusted R square, because just by adding additional variables, that can increase our R squared ever so slightly. And that could be a slightly artificial way to increase our R squared. So we often do an adjusted multivariate coefficient of determination, which adjusts for the number of variables included in the model. So adjusted R square is the better one to report out, only because it takes into account the fact that we could artificially increase R squared simply by increasing the number of variables. So how do we choose different predictors? This is where there is a little bit of art in our methodology. This is another reason why it's really important that we specify in advance what our analysis plan is going to be. We can let our models dictate to some extent what we're going to include, but we should set specific criteria by which we're going to include or exclude variables. Decision rules are very different depending on the analysis strategy. There's also differences across different disciplines in terms of standard approach. But usually there's some sort of criteria that we set in advance that, let's say that a variable had to be statistically significant in a simple linear regression to be included in the multiple linear regression. That would be one possible criteria. You could also do it in terms of the contribution to R square, which would be a similar rationale for including or excluding. There also might be times where, based on theory or other reasons, you want to include that variable, even if it isn't statistically significantly associated with outcome. Something like age adjustment would be standard, and not including age in a final model might raise some eyebrows or red flags, even if it's not predicting a lot. And we also have to be mindful that in a multivariate context, sometimes the relationship of a variable could be affecting the relationship of other variables in the model. And so if theory dictates that we should include a variable, we should probably include it. There's different schools of thought on this. For example, economists will tend to throw everything in the model because they're trying to skim pennies off the outcome. And so anything that they can do to increase prediction is considered better. In health sciences, we tend to be more parsimonious, which means we're going to only include the things that are most essential for understanding the phenomenon. Simple is better. And we're also not interested in things that have minimal effects on outcomes. So if something's only has a minuscule increase in risk or a minuscule explanatory power, we're really not interested in those as much. So different schools of thought, but you should have a plan going in as to what criteria you're going to use to include or exclude variables. And note that as you add or subtract variables, coefficients will change, standard errors will change, and our p-values will change. So again, to avoid multiple comparisons, multiple looks at our data, we should kind of set in advance what our strategy is going to be. We can look for guidance from previous research. We can do it based on a working theory of the clinical and biological relevance of different variables. And then again, we can also set criteria based on things like statistical significance or contribution to R square. You should avoid variables that are highly correlated with the outcome. We can get in a situation where we overfit a model just like a correlation that equals 0.95 or something like that, you have to wonder, are we just measuring the same thing twice? And so you don't want to include those kinds of things. We also don't want to include variables that are very similar in terms of their relationship to the outcome, that are highly correlated. We can introduce a problem which is called collinearity, and it causes our models to not converge like they should. So you would normally select one of two variables that are highly correlated in your model. Again, different schools of thought, but there is a point at which if they're so highly correlated, it can actually make your model not very useful. So another approach would be to maximize your R squared with as few as predictors as you can. So what combination of variables would still give you the same level of prediction or same amount of that you're explaining with fewer variables? That would be another way of considering dropping a variable or including. So if you want to see what a variable's contribution is to a model, you could see how much the R squared changed if you removed it from the model. If it only changes ever so slightly, you might consider dropping that variable. Normally, if something is statistically significant, it's probably contributing meaningfully to the R squared. So those rules about contribution to R squared and statistical significance kind of go hand in hand. But again, you should set some kind of rule. As I mentioned before, there are going to be some variables like age that you simply should just have in there. Having age-adjusted results, particularly in health-related outcomes, is the norm. And we expect there to be age gradients with just about every health outcome. There are exceptions, of course, but age would often be included whenever we have that, even if it's categorical age. Likewise, some clinical and demographic variables are routinely retained because of previous medical research. It wouldn't make sense, for example, to not have sex in a study of heart disease where there might be very different effects if we don't consider sex, or many other outcomes could be different as well. So you can use the literature to help you guide you as far as what to include. But again, you could also do it based on some sort of working theory or conceptual model that you have about what's important in terms of the outcome. So what does multiple regression output look like? Here's an example. So we have, again, a single intercept and then multiple coefficients representing different variables. So here our outcome is birth weight in grams. This would be of a birth weight of a baby. And then the sex of the baby would be 174 grams higher if it was a male versus a female. In terms of gestational weeks, it would be 179 grams heavier for each 1 week increase in gestational age. And then mother's age doesn't seem to have a real strong effect based on the p-value. And also, if you look at the coefficient, a 1 year change in mother's age is associated with only a 1.38 gram difference in birth weight, minuscule amount, right? Because a healthy or normal weight would be about 2,500 grams. So, you can think of it that way. So 1 gram, not very much. Now, it would be tempting to say that male sex and gestational age are equally important. If this were correlation coefficients, that would be kind of reasonable to say. But don't forget, with regression coefficients, these are in the original units. So on the scale of going from 0 to 1, female to male, that's worth 174 grams. Okay, and that's as far as you can go on that scale. Whereas gestational age, we're talking about for 1 week, what would be the difference in predicted weight? Well, for 2 weeks, it would be 2 times that. 3 weeks, it would be 3 times that. So again, it's always in terms of the original units. And so we can't make an apples to apples comparison of a coefficient for male sex to gestational age. You could say that being male versus female is equivalent to about a week of gestational age. That would be fair, but you wouldn't necessarily say that one is a stronger predictor than the other. You can look at a couple things. One, you'll notice that the T statistic associated with gestational age is larger than for male sex. That's one clue that actually gestational age is slightly stronger predictor of birth weight, which makes a lot of sense biologically and clinically. But also we could look at our R-square value and see what would happen if we remove gestational age, see how much the R-square value decreased. Likewise, we could do the same with male sex, and we could use that as our criteria for determining which of the two is the more important predictors. So right now we've included sex of the baby, gestational age, and mother's age. And we have two significant predictors and one non-significant predictor. We could choose to exclude mother's age. However, there may be reviewers or others who would want to see that. We'd also want to see what were the crude associations between male sex and the outcome and gestational age and the outcome, and did they change when we included mother's age? There could potentially be some mutual confounding among gestational age and mother's age. Hard to know without looking first at the simple linear regression model. My guess is that mother's age just simply isn't important and also isn't a confounder, but that is something that you really can only examine by looking and taking those intermediate steps with simple linear regression. Another way to interpret this model. So again, we're saying that each coefficient is conditioned on the presence of the other variables in the model. So a biological male at birth is predicted to be 174 grams heavier than a female baby, regardless of gestational age or mother's age. And that would be an appropriate way to interpret this because, again, we've included gestational age and mother's age. So to talk about the male sex coefficient independently is somewhat erroneous. We could also say mother's age is not important in determining birth weight when also considering gestational age of birth and sex of the newborn. However, we could also be more clear about that if we were to run a simple linear regression and say that there was no association between mother's age and birth weight in a crude model. So that's why it's important to maybe do those intermediate models first to see what those crude associations are. That'll help you better understand what's happening in the multi-regression context. So multiple linear regression models are obviously very powerful tools, and we should be really careful to examine the assumptions of there being a linear relationship among our variables. There are other advanced methods that we're not going to cover in depth in this course or at all, but are used by biostatisticians and are things that you would learn if you were to continue studying biostatistics. MANOVA is a technique that allows for multiple dependent variables, and that often comes up when you have similar scales that are measuring the same phenomenon. You can do MANOVA. Logistic regression is a super powerful tool for modeling dichotomous outcomes, which often happens in health sciences and epidemiology, where we have something like disease outcome, yes, no. We can do logistic regression, which is actually an extension of linear regression. It uses what's called a logit link function to allow us to have a dichotomous outcome. But the mathematics of that are very complicated, and the interpretation is also a little bit complicated. But I do encourage you to continue on in your training to understand logistic regression. Finally, there are other models like Cox proportional hazard models, which are used in what's called survival analysis. There is a chapter in your textbook that covers survival analysis. Poisson regression is for count data where there's a Poisson distribution. That's often used for very rare events. And so there are other tools out there that you can use, but all of them are kind of built around the same principles as linear regression in terms of how we select different variables, how we choose variables to include and exclude. There may be slightly different approaches, but overall, the logic is similar. So briefly, in discussing multivariate ANOVA, multivariate analysis of variance actually has multiple dependent variables. So let's say that we have 3 or 4 scales of depression, and we're interested to see if our factor predicts any of those depression scales, okay? Well, those depression scales are probably very similar to each other. So we wouldn't want to run them independently of each other. So a MANOVA would allow us to say, is there a difference on all of these different measures of depression given our independent variable or our factor? Okay. It's often used to avoid making a type 1 error by making too many comparisons on similar outcome variables. This happens a lot in the social sciences or in psychology or psychiatry, where we tend to have competing scales to measure different phenomena. This happens less often in clinical settings. So you won't see MANOVA used that often. But again, MANOVA is for multiple outcome variables. Logistic regression is probably the technique that I use the most as an epidemiologist, only because we think in really simplified ways, which is, do you have the disease or don't you have the disease? And we're trying to predict outcome that way. Again, it's an extension of linear regression that allows for modeling of dichotomous outcomes. It's mathematically complex, but what's nice is that it can generate adjusted odds ratios, adjusted risk estimates in a multivariate model. And so if you're going from 2x2 tables to stratified tables, logistic regression is more powerful in that you can include lots of variables on different types of scales like you can in linear regression. If I were to recommend another thing to learn about in your training in statistics, it would be logistic regression. It's often used, again, in conjunction with chi-square tests, where we have a dichotomous outcome, and we simply want to adjust for multiple factors simultaneously. We can actually get a long way just using stratified analysis, though, using a series of stratified chi-square tests, get similar results. Survival analysis is a whole other ball of wax. It's actually a semi-parametric approach that combines aspects of parametric and non-parametric statistics. And survival analysis is used when we're interested in time to event analysis. So let's say we have clinical data where we have the actual dates of certain events happening. Then we can perform time to event analysis. We can also use this to deal with what we call censored data, where we don't have complete follow-up on people. We're definitely getting into more advanced methodologies and more advanced problems. But survival analysis is something that you will see a lot in the clinical literature, especially in the context of clinical trials, because when we do clinical trials, we kind of artificially stop them after like 2 years, right? Ideally. Sometimes they're even shorter, sometimes they're a little bit longer. But we just kind of cut the data after a few years. And so survival analysis allows us to deal with that kind of artificial censoring and different follow-up times on people. And we use a model called Cox proportional hazards to deal with those kinds of situations. So the assumptions are slightly different, and it does require more advanced training to use that technique. But in terms of your understanding of looking at output that contains survival analysis data, especially Cox proportional hazard model, the coefficients, the p-values, and all those, you can think of it in terms of, are they different from 0? And the null hypothesis would be that the coefficient is 0, and how different is it from 0? You can also use those to generate other measures of effect, like hazard estimates and odds ratios. So multiple linear regression is a very, very powerful tool to model multiple independent variables. The predictive variables in multilinear regression could include interval, nominal, and ordinal level measures. We have to use that dummy coding technique for categorical variables. In some cases, we can simply include ordinal measures in their original form, assuming that the distance between each value has a similar effect in terms of our prediction. The goals of multiple linear regression are often prediction as well as adjusting for confounding. Usually there's one variable that we're primarily interested in as an exposure. We have some sort of hypothesis about an association. And the other variables that we're including are included because we think they might be confounders. That is, they're associated with both the outcome and the thing we're interested in. And we want to thoroughly investigate whether that including those variables alters that association and can explain away what we saw with the variable that we're interested in. Advanced multivariate methods are the next step in your biostatistical training, and there's always more to learn in statistics. Again, the rule here is that you pick the tool that fits the job, that fits the level of measurement, that fits the research question. And the reason there are so many tools available is because levels of measurement vary, study designs vary. It's not to make your life harder. And there are, emerging methods all the time, but what we've covered in this course is enough to have you understand a lot of what is presented in the medical literature. It's enough to get you able to do exploratory analysis, descriptive analysis. And I encourage you to gain practice in using statistical techniques that will set you up for doing other things down the road. Again, once we've gotten some practice, some of the theories about probability, things like the central limit theorem, they're not always forefront in our minds as we're doing these things, but it's important that we ground ourselves in that understanding before we move into clicking on buttons and generating output. But I encourage you to play around with your data, explore, and get used to it, because there's a high demand for people who can do biostatistical analysis. And even if your immediate goals are to be involved mostly in clinical medicine at some level, often you're going to take interest in research. And so hopefully this course has provided you an extra level of insights, especially when you're reading through those tables and trying to understand what all those numbers mean. Hopefully it'll make you better consumers of the research literature. It's been my pleasure to be the lecturer for this course. I appreciate your attention through some complex concepts. I wish you all the best on completing your individual projects and wrapping up this course. Feathering your cap for completing biostatistics. It's never easy your first time through, but hopefully you've come to appreciate how powerful it is. Thank you very much for your attention. Talk to you soon. Bye.